Solar power is growing in popularity around the world, with huge solar farms springing up all over the place. Obviously, solar panels need as much sunlight as possible, but this also means that they heat up, which limits their efficiency at converting sunlight into electricity. This conundrum may now be solved, though, thanks to a clever coating designed by Aswath Rahman and his colleagues at Stanford University.
What we've done is create essentially an overlay, a top layer that can go on top of the solar cell that does two things. First, it lets through as much sunlight as you would normally have go into a solar cell. So you obviously can't reduce that because that would reduce the amount of power the solar cell could generate. And then second, if you looked at this overlay, this surface, in the infrared, so for example using night vision goggles or a thermal infrared camera, you would see that it looks black, which is to say that it's a nearly perfect emitter of what's called thermal radiation. And this is the heat that we all send out to each other constantly. All objects send out to each other. That corresponds to your temperature. Once you have these two things, you basically have something that allows you to make use of sunlight but maximally send out heat to the sky and therefore to space.
What is this film made of?
So this film is made of silicon dioxide, which is the main component in glass. That's perhaps unsurprising because glass is what's put on top of most solar modules to protect the underlying solar cell. But what's different is that we've actually put in a pattern into the glass. Patterns that are 6 microns apart and about 10 microns deep, and so a micron is about a millionth of a meter, so it's quite small. What they effectively do is create a gradual change of the refractive index between the glass and the air, specifically at those infrared wavelengths where the glass and all objects at typical Earth temperatures are actually sending out their heat in the form of thermal radiation.
So they're kind of acting like a little radiator for the infrared.
That's correct. It's basically something that is extremely good at sending out its heat, like a lot of objects out there, but it's also transparent to visible light. That is a key part of sunlight, which powers our solar cells.
How expensive might it be to develop these kind of coatings for solar panels?
They are expensive at small scales. However, there are techniques to really be able to do this in a very cost-effective way at large scales. And it's really the product of the last couple of decades of progress in nanotechnology in general. More encouragingly, I think the underlying concept here can be achieved by, we think, a different set of potential tools, including multi-layer films, which are nowadays deposited at enormous scales at extremely low cost. So there are definitely opportunities to do this in a cost-effective way.
What kind of benefits could this actually bring? How much could it increase the efficiency of a solar cell?
In practice, in the field, what we think is we should be able to get anywhere from 0.5% to 1% increase in the absolute power conversion efficiency of a solar cell. So what that means is maybe a typical solar cell that's out in the field is about maybe 21% efficient and converting sunlight into electricity. This would give it a boost up to 21.5 or 22%. Now, that may seem like a small number, but if you multiply that by the amount of energy that's out there, it's actually enormous, and it's additive to any other efficiency improvements you can put into the cell.
So if you're thinking about, say, a huge solar farm in the desert, this could potentially make a really big difference.
That's correct. So in solar farms in the desert, the operating temperature of a cell might be extremely high. It might be 60 or 70 Celsius or even higher. And there they do really take a hit and a penalty from operating at such high temperatures. But of course, those are regions where the sun is high in the sky, and they're throughout the year. So they're also where you probably get the best return for your money for putting a solar cell out there.
Aswath Rahman from Stanford University, and that work was published in the journal PNAS.